Hello everyone. Today I'm going to talk about the Helmholtz equation. So here is the actual, it's not the Helmholtz equation yet, but we do have the general classical form of the wave equation here. So this is simply the wave equation. I don't want to confuse anyone because I'm going to take this and actually sort of deduce what the Helmholtz equation is using the wave equation, because this again along one dimension is used to describe any given wave that's oscillating at a particular frequency throughout time, for both position and time. This is what this second order differential equation tells us. But the Helmholtz equation, it's another partial differential equation. However, it's simply a differential equation, again second order, that represents a time-independent form of the wave equation. So this is not time-independent, so this is sort of time-dependent, obviously, given this d2 by dt squared. So this is time-dependent. There's time dependency here for the solution, but in the Helmholtz equation there isn't. And so how do we really get there? So to get there, the first thing that we actually invoke is the separation of variables technique. And if you haven't heard of the separation of variables, I would encourage you to sort of look this up. It's a fundamental topic in especially in your calculus series courses that you take in undergrad. You see it quite often, actually. It simply says that when you have one variable fixed, if you could fix one variable and vary the other, you can successfully separate those variables and in fact introduce them as such. So if we have u of z times z, times u of zt, you can effectively separate these variables as y of z, and here I'm just introducing these two new variables, and t. I'm going to have, oftentimes when you use separation of variables, you use capital letters, and so you have y of z and t of t. So what this essentially is right here is I'm rewriting this form of the equation, or this form of the wave solution, in terms of its time independent parts, its spatial dependent part, and its time dependent parts. And the multiplication of the two gives us our full wave equation. And so I'm rewriting it as yt and t of t. And if we substitute this in, we have d2 over dz squared is equal to y of z, t of t is equal to 1 v squared d of t, y of z, and t of t once again. And so here, since I'm taking a differential of t, I can't really substitute this out or divide this factor out, but I can certainly divide the y. And likewise over here, I can divide the t to the other side since I'm taking the differential with respect to z. And so I'm left with d2tz squared of y of z, and then I have a 1 over y of z out front, which cancels out with this term here. And this is equal to 1 over v squared of 1 over t of t times d2 dt squared dt. And actually, since t is only dependent, capital T is only dependent on little t, and this is a z here, and capital Y is only dependent on z, this is no longer a partial differential here, because you can't. I mean, the essence of partial differential equation, a partial differential equation, is that you're only differentiating along one axis or along one axis in that given function. But here, since this function y, capital Y, is only dependent on z, I can't take a partial differential. I'm only taking a differential equation with respect to z for in the case of y. Likewise over here with t, I can rewrite this as just a normal derivative, double derivative. like that. So I hope that makes sense. And a part of, like, fundamental to the argument of, or fundamental to the use of the separation of variables technique is that when you have one side of the equation equal to one function, or to one side of the equation dependent on one variable, in this case z, so I'm going to say dependent on z, and you have the other side of the equation only dependent on another variable, t, then this separation of variables technique, and you can prove this, tells us that each side has to be equal to a constant. They have to be equal to a constant because the variation in z doesn't change, doesn't mean anything to t. And the variation of t doesn't, have any implication on z. And so if they're equal to one another, which is what we're saying here, they're equal to one another, then both sides of this equation by necessity has to be equal to a constant. And there's ways of proving this. And if you go through the separation of variables, this is made clear, and this fact here is reiterated over and over again. And so we're going to set this equal to a constant, and we can set this equal to any constant we like. That's actually quite arbitrary but it turns out, and you can verify this through the units and how the units play out, that this function here, and likewise for this, or this differential equation here, and likewise for this differential equation up here, is equal to the a constant that we call k, and this is known, and we'll get into this in more detail later, as the wave vector. This is the wave vector. So it turns out that when you take the double derivative of some wave, like so, you get this wave vector term out front. And as you can tell, if I multiply both sides by capital Y of z, I end up with d squared, or I keep writing this differential, sorry about that. It's not a partial anymore. So I have d squared of y of t, or of not of t obviously, of z, dz squared is equal to minus k squared times the y of z. And once again, this here is an eigenequation. This is an eigenequation. So you take this double derivative of y, and out comes some value, some constant, times the same function y. This is a double derivative, or this is an eigenequation. So you have eigenfunctions, which are y's, eigenfunctions, or eigenstates. This is our eigenfunctions, or our mode. You can think of this as a mode. And this is our eigenvalue. And this, ladies and gentlemen, is what is known as the Helmholtz equation. It's nothing more than this. It's the time-independent part of the wave at a fixed k. And we know that, taking this k here, it turns out that this k, this term k, is related to the wavelength, of the wave, of the actual, our wave y of z, our time-independent part of the wave, y of z. It's equal to 2 pi over lambda, where lambda is our wavelength. This is the definition of the wave vector, by the way. So that's how that looks like. And, here we have units of 1 over meters, of course. So we have 1 over meters. That's our units. And if you actually, and I'm going to give you these expressions in this relationship right now. If you recall the definition of, back in the case of the wave equation, actually, when we deduced the wave equation up here, when we deduced this term here, this v, and you can go back to the previous lectures, we established that v squared was actually equal to was actually equal to T over mu, where T was the tension of the rope of the wave. So you have like this wave here, and you have the tension here. That's at every single point. You have an equal opposite force, you know, of T equal to T. And here you have this so-called mass density. Well, it turns out that this term is also equal to omega squared over k squared. And you can check out, and you can check for yourself that the units do indeed make sense here. So this omega squared, the relationship between this velocity term, which we've established this velocity, and we saw how T over mu had units of 1 over seconds squared. This omega and k is related to the velocity as obviously as you know, the reciprocal of one another. So so omega over k gives us our total velocity. So here we see that our velocity units are 1 over meters, and here we see that our omega, our angular frequency, is has units of 1 over seconds. Right, so this gives us meters over seconds. So it kind of makes sense that you have the frequency of your wave and the wave number, right, which is essentially just determined using the wavelength. So if you know the wavelength, you know what this is, right? You get meters per second. This can obviously also be rewritten as you know, 2 or just omega over 2 pi times the wavelength, right? This also gives you the velocity. And if you actually convert omega into its terms of frequency, so 2 pi f, so this is a frequency. 2 pi f is obviously equal to omega over 2 pi times lambda. We end up with the frequency times lambda. So this makes a lot of sense, right? You have the frequency of the wave times its wavelength. That's going to give you the velocity. So you have meters times 1 over seconds. Right? So story is that we have our eigenequation up here, which is our Helmholtz equation, and so this is this concludes this particular lecture. After this, we're actually, the reason we discuss Helmholtz equation to begin with is because we are going to get into standing waves just after this. And so I'll see you guys in the next video.